Imagine hitting a wall of fire at the edge of our solar system, a barrier roaring at 50,000 degrees. In 1977, NASA's Voyager probes launched on a mission to the outer planets, but their journey didn't stop there. Decades later, they pierced the veil of our solar system and sent back data that left scientists speechless. They found a superheated, turbulent frontier that reshapes everything we thought we knew about our place in the galaxy. Let's explore this together. The mission begins. What if you launched a mission planned for 5 years, and it was still sending back groundbreaking data almost 50 years later? That's the story of Voyager. In 1977, NASA launched the twin spacecraft Voyager 1 and 2 to take advantage of a rare planetary alignment that happens just once every 175 years. This grand tour alignment allowed them to use gravity assist to slingshot from one gas giant to the next. The mission was overseen by project scientist Dr. Edward C. Stone, who guided its scientific vision for an incredible 50 years, from 1972 until 2022. His leadership was pivotal as the mission's scope expanded far beyond its original goals of studying Jupiter and Saturn. Voyager's instruments revealed the first active volcanoes beyond Earth on Jupiter's moon Io and the complex braided nature of Saturn's rings. Voyager 2 then went on to give humanity its first ever close-up views of Uranus and Neptune, discovering new moons and powerful winds on these distant ice giants. Beyond the science, the mission also carried a message: the Golden Records, 2 phonograph records containing sounds and images selected to portray the diversity of life and culture on Earth. Dr. Stone and the team ensured that Voyager was not just a scientific probe, but an emissary to the cosmos. This dual purpose has made its journey one of the most profound in human history. Journey outward. How do you measure the breadth of a star from billions of miles away? For decades, the Voyager probes did just that, charting the weakening pulse of our sun. After completing their planetary tour, both spacecraft continued their journey into the vast, uncharted territory of the outer Heliosphere, the immense magnetic bubble inflated by the solar wind. This solar wind is a constant stream of charged particles, mostly protons and electrons, flowing outward from the sun at over 1,000,000 miles per hour. A key instrument for this phase of the mission was the Low-Energy Charged Particle Detector, or LECP. Dr. Stamatios Tom Krimigas, a principal investigator for the LECP instrument, played a crucial role in interpreting the data from this incredibly distant region. His instrument essentially tasted the particle environment, measuring the intensity and direction of these particles. As the probes flew further out, the LECP confirmed that the solar wind was slowing down and thinning out, just as theories predicted. Scientists knew that eventually, this solar wind must collide with the interstellar medium, the tenuous mix of gas, dust, and cosmic rays that fills the space between stars. This inevitable collision would form a boundary, the Heliopause, marking the true edge of the sun's influence, and Voyager was our first shot at touching it. Crossing the Heliopause. Imagine being the first to cross a frontier that was, until that moment, purely theoretical. In August 2012, that's exactly what Voyager 1 accomplished. After a 35-year journey covering more than 11 billion miles, it finally punched through the Heliopause and entered interstellar space. Its twin, Voyager 2, followed a different path and crossed the boundary in November 2018. This second crossing was vital, confirming the findings from a different location and time. The moment of crossing was confirmed by several instruments, but the smoking gun came from the plasma wave subsystem. Dr. Donald Gurnett, the instrument's principal investigator, analyzed a distinct signal, a clear vibration caused by the much denser plasma of interstellar space. Gurnett described it as hearing the sound of interstellar space, a persistent hum that proved Voyager 1 was no longer in the tenuous solar wind, but was now flying through the denser medium of the galaxy. This was a monumental achievement in human exploration, turning the abstract concept of the Heliopause into a measurable, physical place. For the first time, a human-made object was directly sampling the stuff between the stars, and the data it sent back was about to get very, very strange. The Wall of Fire. What if you found a wall of fire at the edge of the solar system? That's the poetic yet scientifically accurate description of what the Voyager probes encountered. As both spacecraft crossed the Heliopause, their instruments detected an astonishing and abrupt spike in the temperature. The plasma in this boundary region was heated to between 30,000 and 50,000 Kelvin, which is roughly 54,000 to 90,000 degrees Fahrenheit, far hotter than the surface of the sun. This discovery was a complete shock, as most models predicted a much cooler, more placid boundary. The data came from multiple instruments, including the magnetometer, which measures magnetic fields. Dr. Leonard Berlage, a key member of the Voyager magnetometer team, helped analyze how the magnetic field lines bunched up and compressed at this boundary. This so-called wall of fire isn't a literal flame, but a region of extreme heating caused by the solar wind essentially slamming on the brakes. As it collides with the dense interstellar medium, the kinetic energy of the particles is converted into thermal energy, a process known as compressional heating. The finding sent many theorists back to the drawing board, forcing a major revision of our understanding of how stars interact with their galactic environments.
A superheated frontier.
You might wonder, how could a spacecraft survive flying through a region that's tens of thousands of degrees hot? The answer lies in the critical difference between temperature and heat. Temperature measures the speed of particles, while heat is the amount of energy they transfer. While the particles in this wall of fire are incredibly hot, meaning they are moving at immense speeds, the plasma itself is incredibly sparse, far less dense than the best vacuum we can create on Earth. We're talking about fewer than 1 particle per cubic centimeter. Because the density is so low, these super-fast particles almost never collide with the spacecraft, meaning almost no heat is actually transferred. Dr. John Richardson, the principal investigator for the plasma science instrument on Voyager 2, was instrumental in analyzing this data. His team's work showed that while the temperature was extreme, the pressure was negligible. It's like the difference between the air in a hot oven and a drop of boiling water. You can put your hand in the oven for a moment, but the water would instantly scald you because its density allows for rapid energy transfer. This superheated, low-density frontier provided our first direct evidence of this turbulent transitional layer where the sun's influence finally yields to the vast expanse of the galaxy.
The dynamic shield.
What if our solar system had a protective shield that breathes, expanding and contracting with the sun's rhythm? The Voyager missions revealed that the Heliosphere acts as just such a shield. It's a vast magnetic bubble that deflects about 75% of the galaxy's most energetic cosmic radiation, making the solar system a much safer place for life. The work of theorists like Dr. Randy Jaquipi, who spent his career modeling how cosmic rays propagate through the solar system, provided the framework for understanding this mechanism. The data from the Voyager probes turned these theories into observed fact. One of the most fascinating discoveries was that this shield is not static. Voyager 1 crossed the Heliopause at 121 astronomical units, while Voyager 2, on a different trajectory and at a different time, crossed at 119 AU. This difference, though small, was monumental. It confirmed that the heliosphere breathes in and out with the sun's 11-year activity cycle. During solar maximum, when activity like sunspots and flares is high, the solar wind pushes harder, and the bubble expands. During solar minimum, it contracts. This discovery fundamentally changed our view from a static boundary to a living, shifting shield that responds directly to the heartbeat of our star.
Magnetic mysteries.
Imagine expecting a sharp, dramatic change at a boundary, only to find a smooth, almost seamless transition. That's what Voyager discovered about the magnetic fields at the edge of our solar system. For years, scientists had predicted that the magnetic field inside the heliosphere, which is carried outward from our sun, would be oriented very differently from the interstellar magnetic field. The prevailing models suggested that as the spacecraft crossed the heliopause, it would see a dramatic shift in the field's direction, a phenomenon known as magnetic reconnection. But that's not what happened. Dr. Norman Ness, the principal investigator for the magnetometer instrument on Voyager 1, was at the forefront of this surprising discovery. His instrument, a sensitive device on a 13-meter boom, found that the magnetic fields on either side of the boundary were nearly parallel. This unexpected finding implies a much smoother connection between the solar and galactic magnetic environments than anyone had predicted. Instead of a sharp, defined edge, the boundary appears to be a more gradual blending zone where the sun's magnetic influence slowly intertwines with the larger magnetic field of our local galactic neighborhood. The mystery of why these fields align so neatly is still a topic of intense debate today.
Cosmic ray barrier.
How does our solar system defend itself from the constant barrage of high-energy particles from deep space? The Voyager missions provided a ringside seat to this cosmic battle. Galactic cosmic rays are atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light by distant supernovas. They are a form of powerful radiation that can damage electronics and living tissue. The heliosphere acts as a semi-permeable barrier against them. Dr. Frank B. McDonald, a pioneer in cosmic ray physics and a key scientist on the Voyager mission, dedicated his career to understanding these particles. His work, combined with Voyager's direct measurements, gave us an unprecedented look at how this shield works. As Voyager 1 and 2 neared the Heliopause, their cosmic ray instruments detected a dramatic increase in the intensity of these galactic particles, confirming the heliosphere was indeed blocking a significant portion of them from reaching the inner solar system. At the same time, they saw a sharp drop in the number of lower energy particles originating from our sun. This data is not just academic, it directly helps us refine models to predict the radiation environment for future crewed missions to the Moon, Mars and beyond, ensuring astronaut safety.
Interstellar Space.
What is the shape of the bubble that surrounds our solar system? For a long time, the prevailing theory was that the heliosphere was shaped like a comet, with a rounded nose and a long, trailing tail stretching for billions of miles behind it. But the data from the Voyager probes, combined with observations from other spacecraft like Cassini and Ibex, has challenged this simple picture. Dr. Merav Ofer, a leading heliophysicist, has used this data to create new models suggesting the heliosphere may not have a long tail at all. Her research suggests a shape more like a deflated croissant, with two large jets of solar material flowing downstream, shaped by the pressure of the external interstellar magnetic field. This new model is still being debated, but it shows how Voyager continues to fuel new scientific inquiry nearly 5 decades after launch. The faint signals from the probes, traveling for over 22 hours to reach us, provide our only direct measurements of the interstellar medium. This information about plasma density, magnetic strength, and cosmic ray intensity is the ground truth against which all our theories about our cosmic home must be tested. Each bit of data is precious, a postcard from an unknown shore.
Future missions.
Where do we go from here, now that we've taken our first steps into interstellar space? The Voyager probes were technological marvels of the 1970s, but they have also raised a host of new questions that can only be answered by a new generation of explorers. NASA is already conceptualizing a follow-up, a dedicated mission aptly named the Interstellar Probe. A key figure in developing this concept is Dr. Ralph McNutt of the Johns Hopkins Applied Physics Laboratory. The proposed probe would be designed to travel much farther and faster than the Voyagers, using a next-generation power source and a powerful launch vehicle to reach speeds that would get it to the Heliopause in about 15 years, not 35. It would carry a suite of modern, more sensitive instruments capable of mapping the full three-dimensional structure of our heliosphere and studying the interstellar medium in unprecedented detail. One of its primary goals would be to solve the mysteries Voyager uncovered, like the wall of fire and the parallel magnetic fields. Such a mission is crucial to understanding whether our heliosphere is a template for other star systems, and what truly makes a planetary system habitable in a galaxy full of radiation. From a grand tour of the outer planets to a journey into the interstellar void, the Voyager mission has fundamentally rewritten our understanding of the solar system's edge. It revealed a dynamic, superheated frontier, a place not of emptiness, but of incredible energy and motion. The two probes, now nearly 50 years into their mission, continue to send back faint whispers from the darkness, each signal a new piece of the cosmic puzzle. Though their power will one day fade, their legacy will endure, carried on the golden records that drift silently between the stars. Don't forget to like, subscribe, and hit the bell icon for more journeys to the frontiers of science. Thanks for watching InnoVision Tech.